All right, we're going to go ahead and get started just to stay on track with time. I'm sure people are running behind. So, my name is Heather Wooden. I'm the IEST Meetings and Education Program Coordinator here at IEST. So, if you aren't aware who IEST is, we're a membership association that gives technical guidance to professionals working in controlled environments. We help to develop, write, and publish industry recommended practices through our working groups. And then we are an ANSI, which is an American National Standards Institute standards developing. And we are the secretary of the International Standardization Organization's Technical Committee 209, which is cleanrooms and associated controlled environments. And we're also the administrator of the ANSI accredited U.S. Technical Advisory Group to this technical committee. So today's webinar is going to be a spotlight on the new ISO 14644 Part 4 standard. So it's going to be pretty informal. Wei is going to go ahead and give his presentation. If you have any questions throughout the presentation, go ahead and type into the chat box. The chat box is going to be located on the lower right-hand corner of your screen. You can click that to open up the chat box and type in any questions that you may have. So I'm going to go ahead and introduce our presenter for today. Wei Sun is the ISO 14644 standards US delegate for Working Group 4 and also Working Group 16, which is on energy conservation and clean rooms. He has served as the chair of the ASHRAE Technical Committee, TC 9.11 until 2010, and a voting member of ASHRAE TC 9.10 and TC 9.9. He's an ASHRAE Fellow and ASHRAE Distinguished Lecturer. In addition to his design experience for large clean room, lab, and healthcare projects, he has been serving as a principal investigator for many governmental research projects. And he has served with IEST as a president, as well as our technical vice president as well. So I'm going to go ahead and Wei, have you go ahead and take it away.
Thank you, Heather, for a very nice introduction. It's my pleasure to have a time during your lunchtime and to have a introduction of the new ISO 14644 Part 4. And just a very brief introduction of myself. Many of these elements being indicated by Heather, and heavily involved with IEST activities, and also serving ASHRAE currently as a director at large. And I was the principal author for the ASHRAE Clean Room Design Guide. And in addition to ISO, I also serve as an NEBB chairperson for the CPT standard, Clean Room Performance Testing. And I'd like to give a quick background about the 14644-4. And the first edition was published in 2001. The second edition, which is the current, was published last year. And ends upon IEST as the administrator of the US Tech TC 209. And the current chairperson of the ISO TC 209 is Gordon Ely. He was a past IEST president. And Mikey Milky is the committee manager for TC 209. And I believe 2000 he was IEST vice president. And Emery Dixon, who was the president in 1991, is the current chairperson of the US Tech to the TC 209. And Jennifer Skinner is the IEST staff, is the secretary of the TC209. And we have 2 US experts, myself, and also Norman Goldschmidt. And we have many countries involved in this Part 4 development. You can see the country are listed. So it's an international and a global effort. And, since the last edition was 2001, and virtually is about 21 year past. Lots of progress and advancement in technology application and a design concept. So I'd like to use this opportunity to give the more detailed discussion. If you look at the cover page, not much difference. Basically, is the replacement of the year, and we did some restructuring. These are the previous content, requirement, planning, design, construction, startup, training and approval, documentation, and many appendix or annex. And we restructured the system slightly differently. And used to be the planning and requirements. Design, we have a designated chapter for design and a designated chapter for construction and startups. Then we have a fewer annex, but it's a more consolidated and structure in a much easier, much reader-friendly way. And the annex, basically, these are informative. The other sections in the main body, this is what we consider is the normative. Flow chart, so basically is that we have a chapter 6 for the requirement, which Annex A provides supplementary information. Chapter 7 is for the design. You have a conceptual, basic, detail, and Annex B support and provide more supplementary information. Chapter 8, which is for construction. Annex C is supporting that. And Chapter 9, startup, including commissioning, training, and a handover, where the Annex D provide additional information. If we look at the basic elements for this ISO standard, so basically it's very similar as what we have for the -1 for the Part 1. We have 3 key variables: particle size, so cleanliness class, and the respective threshold of particle concentration. So each ISO class have a maximum allowable counts at each specific particle size. During this new standard development, we introduced and also clarify certain concepts. For example, we divided in 3 categories: contaminant source, contaminant transmission, and migration. Regarding the source, introduce a concept called the strength reduction. Basically, strength is the source is the particle generation from people, from equipment, from process, even for the architectural components, such as wall, floor doors, all these generate particles. So the source control is you can do either reduction, isolation, you confine these and take as much particle out as possible before you let them to migrate into the rest of the room, and also removal. If you generate it and you need to localize and provide a removal capacity, so to minimize the particle dispersion from the source to the rest of the room. So if a contaminant escape into the room, then you have to do the we call it the dilution to reduce the concentration, particle concentration in the room by providing the filtered HEPA filtered supply air. So these are the source. And regarding the transmission, one is to keep the distance from the source. If you have a critical operation, you want to keep a distance from the source so you have a less chance to be contaminated. And also the airflow cascade. You want to provide a certain kind of upstream, midstream, and downstream. Make sure the clean air flow from upstream, downstream, and then to the midstream, then to the downstream. So you provide a certain cascading effect. And also to control the contaminant migration or particle migration, one is to do the pressurization or depressurization. To intentionally direct the leakage airflow direction. The other is to use the airlock. So this new ISO standard, we put it in 3 different categories to clarify some concepts. New information we added. The final design we review against the requirement for construction. And when the construction is completed, the operation and the performance is verified against the requirement during startup. Also, identify the critical control points in a clean room or a clean zone, not just the average room concentration. The whole idea is measure at multiple locations in a clean room, you average them, then you take a look to see if you pass, if you are within the ISO 7 or ISO 8 or ISO 5. In addition to the average value, which is very important, you also need to pay attention for the critical control point, especially those during the process critical area or spots. These are the area the customer may need to have additional requirement. For example, the room, they may want to have ISO 7, but at the adjacent of this critical process area, they may want to have ISO 6 and just give some kind of additional margin or cushion to ensure that the critical locations will not fall below the ISO 7 level. And also this standard uses the calculation formula instead of using table method for the air supply rate, which also means the air change rate for the contaminant removal. Others we use the table method for decades, but now ISO is kind of gradually move on from the table method and use a formula to estimate, to calculate. And also this new standard introduced the idea or called the importance of the ventilation effectiveness through control of the airflow pattern and cleanup recovery rates. There are 2 measures for the ventilation effectiveness, which will be used as a correctional factor. You calculate the air change rate requirement or the airflow or air supply rate requirement. One is the air change effectiveness, ACE. The other is the containment removal effectiveness, CRE. And so in this new ISO standard, you have these 2 new we call the ventilation indexes, which will be used as a correctional factor when you calculate the air change rate requirement or air supply rate requirement. And also this standard incorporates some idea from the ISO 14644 Part 16, which is the energy efficiency in clean room and a clean air devices was published 3 years ago. And so I'll use a lot of information from that standard into this -4. So energy efficiency and life cycle consideration is a part of this new standard. And also, clean room have been kind of slightly redefined, and room within which the number of the concentration of airborne particles is controlled and classified, and which is designed, construct, and operate in a manner to control the introduction, generation, and the retention of the particles inside the room. So world of control basically is to reduce the introduction, reduce the generation, and reduce the retention. So once you have a particle generate, first of all, you want to minimize as low as you can. And second is to reduce the introduction from location A to location B. And also to minimize the particle migration from the adjacent space. Reduce the retention is once you generate it, and you will find the effective way to let a particle to exit, to return, or exhaust airstream. So this new standard use more clarified language, put into different category, so design engineer can put more attention, say, by this new treatment or activity or effort is going to reduce the generation or reduce the introduction or reduce the retention of the particles. So they know what's the purpose of these efforts. And also the new standard specifically say the airborne class need to be specified, and the level of the other cleanliness attributes such as the chemical concentration, viable, or even nanoscale contamination need to be listed if required by the customer. And also the concentration in the air, including the surface cleanliness, particle, nano, chemical, viable, also need to be specified or controlled. Once you specify, then next is to find ways to control them. And, the relevant physical parameters, such as the temperature, humidity, pressure, vibration, electrostatic. If all these other elements or parameters need to be considered, so these need to be listed, specified, and find ways to control them. And also, the source strength is the first time as a terminology being introduced in this new standard. So basically, number of airborne particles or other contaminants are considered and emitted per time unit expressed as a rate. So via particle could generate from person, equipment, and object, such as the building components, the processing itself, and also very important that each rate should be indicate the specific particle size, since the particle emit in multiple sizes, not in a singular size, on the multiple sizes, and each size may have a different attenuation rate. So not just a singular size, not at a uniform generation rate. Different size may generate at the different rate, and so this is what we call it the profile. At a specific size, you can measure at the site to see what's the level of concentration, which means what's the source of nearby that generate and a contribution to this concentration level. And also the design being is divided into a 3-stage: conceptual, basic, and detailed. And material, product, personnel, waste flow diagram need to be overlapped on the layout and with the descriptions. So you have virtually you have a full flow diagram, or we call it traffic passage, for material, for product, for personnel, for waste. So design engineer need to check to see these 4 flows, they are not conflict each other or cause additional concern of the contamination control. And regarding specification, air cleanliness level, airflow control concept, temperature, relative humidity, pressure differential, zone segregation, and we will talk more about the segregation method, airflow, and also on a schematic, the airflow diagram, room pressure setting, room air balance, how much air in for each room, supply air, how much return exhaust, any leakage air, which the leakage air direction. All this need to be indicated on the layout, on the floor plan, and what's the pressure level. You know, may have a multiple stage of a pressure. You know, high, medium, low, neutral. Some room could be in negative pressure, so we call it pressure cascading. And so all this need to be indicated. And automatic or manual control to achieve required airflow rate, air flow direction between rooms, and a pressure cascade. Lots of information in this statement. So you can do a manual control or automatic control, and to achieve the required flow rate. So if you do automatic control, you can have you know, some kind of flow modulation device deliver the required flow rate for each clean rooms, and also airflow between rooms, which is the leakage airflow, high pressure leak to the low pressure area. So all this airflow direction need to be indicated on drawings. And supporting calculation to confirm airflow necessary to achieve required level. So in Annex B, they provide more information. And also, another emphasis is on the recovery rate or recovery time. And since dash 3 testing required to have a recovery test, measure both the recovery rate or recovery time. And so in some design documents, especially for pharmaceutical industry, sometimes recovery time need to be considered as a part of the design and eventually need to be tested dash 3 standard to see how long going to take that room to recover to the original previous level. And also the description of sequence of operation relating to the critical performance parameter to aid the designers and software development. So in all days, sequence of operation very simple. So now there is a new trend. Sequence operation can be well embedded into the computer software. And now there is a new trend for the adaptive control, even the AI control. So when design engineer writing down their sequence of operation, some of these could be incorporated into the control logic algorithms into the software. And also this standard indicated that the first time that a building management system, BMS, is a part of the consideration because nowadays almost, I would say not 100%, but at least over 95% of these clean room facility either have an independent BMS system or a clean room suite, could be incorporated into a building automation or building management system. Performance monitoring, some it's being added into the new standard. Cleanliness attributes, performance parameter, we already talked about this, and also the test and measurement method and their frequency. Also very important is the real-time continuous performance monitoring and the trend analysis. Action and alert limits when appropriate or if appropriate. And so basically is that now there is a lot of a facility as a part of their quality control efforts, and in their critical zone or area, many facilities they install real-time continuous, let's say, laser particle sensors to monitor the real-time concentration, not just rely on every 6 months field testing by certifier like NBB or other organization. So they bring in the test instruments, see what's the ISO level, what's the average room particle concentration, and then give you a table or give you a certification form. But what about during the 6 months gap? Let's say we finish the certification, you certify this room ISO 5, ISO 7, then 6 months later, test it again. What about what happened between these 2 points? You look at the time scale, anything could happen. HEPA filter could be damaged. Some people accidentally poke the HEPA filter, and then you don't have ISO 7, ISO 5 anymore, but you do not know until 6 months later. So now ISO uses the word called a real-time continuous performance monitoring, is that you can put a laser particle sensor to monitor the real-time condition 24/7, 365, in addition to independent manual field testing and certification. And also, since you do a continuous monitoring, you also can do a trend analysis. You can look at on a daily basis how your particle concentration, what's their change profile. So that provides more information for the performance and quality control. And there is several concepts for the contamination control. One is zoning. So basically is a box-in-box concept. The critical area you put at a higher pressure, usually in the more inner center location. The on-site zone will be less clean, and then when layers on further on-site will be could be even non-classified area. So you have a flow for material, flow of the product, flow of the waste, and a flow of personnel in and out. All this need to be indicated on the design documents. And second concept is the physical barrier and the airflow segregation. The 3 concepts in this new standard. First is a physical barrier with the leakage static pressure P1 higher than P2. So you have a 2 room separated by a wall. It could be a minor X for that wall, for pipe, for conduit penetration. You may have a caulking or seal, but it usually is not very airtight. So air can leak under certain pressure. So this is the time your door is closed, so air still can leak from high pressure clean room to low pressure clean room, which will cause particle migration. The second is you still have a minor leaks, but you open a doorway. So in this case, you have a leakage, and also have an overflow through the doorway. So room 1 you have a high pressure, and then room 2, you have two passages. One is through the minor cracks, the other is through the major doorway. The third is dynamic segregation. In this case, there is no practical pressure difference between area A1 and area 2. For example, but the air cleanliness level could be different. One, let's say area 2 may be ISO 8, area 1 may be ISO 7. One example is the what we call the demarcation bench in gunning room. One side is cleaner, on the other side dirtier, and there is no bench. You can walk across. There is no physical barrier above it. So basically, we use different airflow intensity. Cleaner area, we use more air change or higher velocity. Less clean area, we use lower intensity or lower velocity. But if you measure the pressure, they may not have a significant difference. But air cleanliness could be different. Another example is surrounding a surgical bed or zone in operating rooms. In operating room, you have a surgical bed. Surrounding area, you have almost 100% HEPA filter above it. And in the surrounding area, on the perimeter of the room, you have a less HEPA filter. So in the surgical zone, you may have ISO 7 or even ISO 6. In the surrounding area, you may have ISO 8. So you can create some kind of air cleanliness difference without physical barrier. One way to do it is to provide a different airflow intensity. Concept 3 is what we call the displacement and the dilution. Displacement basically is to utilize the unidirectional flow. Dilution is use a non-directional flow. In the previous first edition of the standard, they provide a lot of diagram, conceptual charts. But in this standard, the committee member decided to simplify the concept, and so use a unidirectional. Basically, is a displacement. You provide a clean HEPA filter air at the top, and you release at the low sidewall grill or raised floor grill. So basically, you push the air out. Whichever, how much particle you generate, they use more like a piston effect. Anything generate, we take them out. This is usually for ISO class 5, cleaner class. Lots of other rooms, they use we call it the dilution method. It's a non-unidirectional. It's not but not really good in parallelism. So they have lots of eddy flow. The seating not really 100% HEPA filter. They may have a 10%, 15% coverage by HEPA. And so there was a lot of eddy flow. So the objective of the non-unidirectional flow basically is the dilution. It is like a fish tank. You have a fish, all right, they generate the waste. So if you do not have a filtered clean water in and drain the same amount of water out, the water will get dirtier and dirtier. For clean room, it's a very similar concept. You cannot visualize the particles, but it's a very similar concept as a fish tank. So you need to have adequate filtered clean water in, and you take on the same amount of the water, so you can keep the cleanliness of the water. And so for the clean room, it's a very same concept. Use a dilution. Dilution is of course, it wastes a lot of energy. But once the particle emitted from the source to the rest of the room, It's not reversible. It's not like a disperse into room, you can take them back. You cannot take them back. You do the dilution, then you use the return and exhaust air stream to take them out. So these are the two key methods. And also is we call a combined flow or mixed flow, is the combination of dilution and displacement. And so where the critical area of the clean room require a better air cleanliness level than the rest. And also, this is very new. The standard introduced a calculation formula for airflow rate for non-unidirectional airflow clean rooms. Method 1, simple dilution equation. U is the supply airflow rate. S is the particle emission or particle generation, which is a source strength. And the C is the concentration limit. If you have a ISO, 7 or 8, you have a concentration maximum threshold. So that's your maximum concentration. And epsilon or alpha is the ventilation effectiveness. We changed the notes several times. So which is a dimension S rational factor. This ventilation effectiveness, as we talked about earlier, could be containment removal effectiveness, or could be air change effectiveness. The official definition defined by ASHRAE and utilized globally. And so this new ISO standard, they introduced this concept into it. The method 2 is the dilution equation with the correctional factors or correctional for two scenarios. One is consider the surface deposition, especially for large floor area, surface area, and a low air supply flow rate. So if you have that case, that VD is the deposition velocity, and typically this the range 0.0037 to 73, and beta is the ventilation efficiency. I'm sorry, the A is the horizontal surface area. So this term as a correctional measure is to consider the particle surface deposition. Sometimes you have another scenario is that you have a separative devices that they have a supply air in, either use a room air or designated air source, but they release the air back into the clean room. If you have that kind of situation, so especially you have a very small clean room, but you have a multiple large separative devices, then you need to have an additional rational measure or method. So the beta is the ventilation efficiency coefficient of the device, separative device, which is the -7, and they have a way to measure the coefficient. Or the manufacturer may have data for that. And QD is the supply volume inside the device. You have a supply air in, but they release this amount of air back into the clean room. So some corrections need to be made to the simple dilution equation. So this ISO standard introduces these two methods for engineers to estimate the required airflow rate. Now, people may ask, how can I get a particle generation rate? There is many sources on that, and this standard provide a detailed list to where to get the data from these multiple reference or sources or publications. And also, this standard introduced the CFD into the design standard. CFD, which is the computational flow dynamics, The modeling can provide a simulated information on airflow pattern to optimize the design and to achieve a more effective and efficient installation. By obtaining the likely airflow pattern, the pre-construction stage, typically during design, you have nothing to test. You cannot do a smoke test because the room is still on the drawing board in office. So to minimize the unforeseen design errors, efficiency, and ineffectiveness, you can use the CFD to simulate based on your design and to identify if in any area you have a effective or a functional area. So more specifically, CFD we need to input the geometry of the clean room, the equipment, where are the heat sources, airflow supply rate, extract rate, extract means return or exhaust, the location of the inlet and exhaust. And so you provide this information into the CFD model. And then you can visualize airflow parameters, airflow patterns, and a containment concentration to identify the areas that have a poor performance. For example, suitable velocity. Some area velocity very high, some area very low, which may be below your requirement. So you can identify during design stage, CFD, say, I may need to relocate a HEPA filter. I may need to add a HEPA filter, or I may need to add more filters. I keep the total CFM flow rate, but I distribute the airflow HEPA filter more evenly. The other thing is identify if any passive eddy flow. Eddy flow means current that it will cause cross-contamination, rotational, and a high concentration of the particle. If you have several spots, you find a very high concentration and also very close to your critical operation or critical zones. So you need to find a way to mitigate them. And also, if we have airflow from less clean area to cleaner area, so typically we want to have airflow from cleaner to less clean, not in the reverse direction. So if you see in the CFD simulation, you found the other direction, then you need to find a way to make a correction. And also, if you have any unsatisfactory containment removal, you have a particle generate, but these particles, they are still dancing around inside the room. They do not exit smoothly through exhaust or return. Then you need to find a way to say, I may need to add more return points. I may need to add return columns to do something to make sure that the particle generated inside can be timely, smoothly removed from the room. And also analyze the ventilation and particle removal at critical locations. And after the clean room is installed, a few verification, a few visualization is required. Typically, we call a smoke test, should be performed to compare and validate the output of the CFD simulation. During design, you have nothing to test. After the installation, now you can do a smoke test. You can compare the smoke test result versus the simulation, CFD simulation, to see if they are in the same story. And so that's also very important to validate the CFD, because CFD by different programmer, they may the very same geometry, the very same boundary conditions may produce a different outcome. So experience of the CFD engineer is very critical. Otherwise, it may pointing you to a different outcome that may not be reflected by your future smoke test. So smoke test still is the required, but CFD is optional. But this is the first time ISO standard have a very lengthy language included into the standard. Other thing is the airlock and a pass-through. This new standard, they use the enhanced concept. In US, typically airlock, we have 4 types: cascading, double, sync, compartment. I'm not going to go detail. ISD actually has in our tutorial, we talk about more technical design issues for that tutorial. So more detailed information could be available through that training. But basically, in this ISO standard, for the airlock and the pass-through in the same category. One is to minimize the transfer of the contamination between the rooms with the different air cleanliness during personnel and material transfer. Every time you open the door, you pass through objects to pass through, we actually have a particle exchange across the barrier. Could be airlock or could be pass through. And so your goal is to minimize it. And the particle migration will happen. Your effort is to minimize it. Maintain the pressure differential between the rooms, ensuring the opposing doors are not open simultaneously. So typically airlock or pass-through, you have 2 doors in series. No standard, we don't say about that you cannot open the 2 doors at the same time. But in this standard, they specifically say you cannot open the 2 doors at the same time, either by interlock or by some electronic means that you have a different light, red, yellow, green, whatever. If the red or yellow, that the second door cannot be opened until it turns green. So this standard, they put more specific language. You cannot open the 2 doors at the same time. And also airborne contamination release inside the airlock or pass-through box to be contained and removed by a combination of interlock doors, dilution by clean supply air, or defined flushing time. So basically, they're saying is that the 2 doors, typically inside the airlock, you are required to have a HEPA filter. So you can provide the clean filtered air to replace dirty air, because every time you open airlock door, particle migration will occur. You cannot prevent it, but you can minimize it. This particle migration in, close the first door, use the HEPA, filter the air to replace the dirty air, big amount, then you can open the second door. So this ISO standard, they use the word called a defined flushing time. In other words, you want to have the particle which migrate from outside into the airlock, big amount, you open the second door. So the time duration between the 2 door operation, we call the flushing time. And so ISO standard put this language in. And so basically it's very simple. The flushing time based on the air change rate inside the airlock. High air change rate, shorter waiting time. And so basically airlock is dependent on the amount of air you supply and the time used to air particle concentration. And so the standard provide more detailed language for this. And also some checklist for design, for construction, for startups, and checklist. This provide much more information than the previous 2001 version. And checklist 2, for example, in this standard, more specifically added the monitoring and control. So real-time online monitoring of conditions in critical zones. Automatic control of room environmental conditions. And a building management system. So this become a more typical nowadays. So the ISO committee decided to put this language in. to match the technology advancement in the real world application. Construction checklist. Construction and a startup, most of these, I would say 95% are pretty much similar as the previous audition. We did some integration or consolidation to make the language more clarified and cook them in a more user-friendly ways or reader-friendly ways. And a startup checklist. Also, I believe IST online bookstore has the new standard dashboard available. And also, I believe the ISO website, they also, I believe, have this standard available for purchase. And in addition to the standards itself, the standard lists many reference in the standard. And one is, of course, -1 and -2, which published a few years ago. That's the basis of this -4. And also, Azure has a handbook chapter 19. By the way, IST will be publishing a new, we call it RP 12.4 this year, and which is provide more supportive information to this -4, but provide in certain area they provide more detailed information. And NEBB will have a new testing standard published this year, and in 2017 actually published a book called a Cleanroom Design Guide for Cleanrooms. Also PDA, which is for pharmaceutical side, they published a book called Cleanroom Contamination Prevention and Control. I have been very lucky, serve as the handbook chair for Azure, working group chair for the RP 12.4, and standard chair for the new 2023 version for the NEBB. And I was the principal author for the Azure Design Guide, and a co-author for the PDA book. So this, I believe this is my quick introduction of the new -4 standard. And we'll be ready to entertain any questions that you might have.
Does anyone have any questions regarding the document? You can type it into the chat box, or feel free to go ahead and unmute yourself and you can verbally ask the question too. Wait a minute. See if anyone types anything in. Don't see.
Ivan, thank you for your comments.
Yeah, I don't see any questions coming in. I
Yeah.
do want to make a note that for anyone that has registered for the webinar that is today, I will be sending you an email. And the email is going to be a coupon code if you are interested, or if you still need to purchase the -4 for a 10% discount on the document. So I will be sending that out within the next couple of minutes to everyone if you are interested. Evan, did you have a question?
Yeah, actually, I was thinking on it. So, kind of interested in the building management system. So, automated controls. Is that particles and AMCs? That include both?
Yeah, that's a very good point. When we talk about the real-time monitoring and building management system, that suggests, in addition to temperature, humidity, pressure, and other parameters, particle constitution also can be controlled automatically. Although there is no detailed information provided in this ISO standard, but there are several research articles by Ashley. Actually, I was the principal investigator on the automatic control of the room air cleanliness to meet the ISO class 24/7 365. And although it's in the earlier stage, but it's feasible.
Okay, thank you.
And then I did receive a question in the chat box. It says, is there any information in there about source strength from equipment?
That's a good question. This ISO standard -4, they indicate multiple reference and publication, and so you can use the publication or reference to identify these source strengths, or we call it particle generation rates. And basically, you have a particle generation rate from people with no gowning, partial gowning, or full gowning. So they give a range of that. And also some kind of key major equipment. And also the activity level personnel sitting there, or minor body movement, still sitting there but moving arm around, or you have slow walking, or you have heavy activity. So all this level, this activity generate a different level of particles, and this reference, they provide more data for that. They typically give you a range, so you can pick some data. In a room, since a particle can be generated in multiple sources, from people, from equipment, from architectural components such as the wall, floor, ceiling, and so total particle generation is the summation of all these sources. It's like a game for when you do a heating cooling calculation. Heating multiple sources, you add them together, that's your total particle generation. Then you plug into the simple equation to estimate. I wouldn't call this is a precise calculation. It's more like an estimate weight. You still can use the old table method to give you a general range. Then use the calculation formulas to see if you can narrow down the range. And yeah, hopefully answer your question then.
Any other questions?
And also, by the way, in addition to what Heather offered for the discount, I'm going to provide a PDF version of my talk today. As long as you order something from Heather, so you can also get a copy for the PDF version for my talk today. This is my very first talk regarding the -4 standard. In the coming months or maybe next year, we'll provide a revised version, and possibly next year.
Great. Thank you so much, everyone that attended, and thank you for all the information that you gave today. And everyone have a good rest of their day. Thank you so much.
Thank you all for your great time. Enjoy.